Great. Well, thank you very much. It's a pleasure to be back at KITP. And I was looking at the last times that I've been here. And back in 2013, I was standing here in kind of a Snowmass-like event, talking about supersymmetric model building and naturalness. And, times have changed. And something that's a surprise to me is that I've become involved in this community thinking about machine learning, mostly for the types of things that Ian was talking about in terms of jet physics. But also in this talk, I'll try to talk more broadly about the relevance of machine learning for the theory frontier. Just as an advertisement and a thank you to the National Science Foundation for funding a new Institute for Artificial Intelligence and Fundamental Interactions, which is a joint venture that I'm directing between MIT, Harvard, Northeastern, and Tufts to, on the one hand, advance physics knowledge, and on the other hand, galvanize AI research innovation and bringing together physicists, computer scientists, statisticians together to try to infuse physics intelligence into artificial intelligence. And so you can take, thank you for the groans. And by the way, you're going to be groaning even more on the next slide. So you can take all the high principles that we've been talking about this week, ideas like symmetries, locality, causality, guarantees of exactness, verifiability, systematic uncertainties, which need to be included in any real measurement. And you can try to see, could those be infused into AI techniques? I believe the answer is yes, and part of this institute is trying to drive that progress. Now, here's where you get to roll your eyes a lot, because when you start talking about physics intelligence and artificial intelligence, you start having New York Times reporters coming and asking questions like this. Can a computer devise a theory of everything? And I am quoted in this article. Okay, this is an interesting representation of a theorist kind of lobby with, I guess, some kind of neural networky thing. And on the one hand, I absolutely loathe this question. Okay, I loathe this question because first, it's overhyping of deep learning, which is just one of many computational strategies relevant for the physical sciences. And also, I'm not convinced that deep learning in the sense of multi-layer neural networks is going to get us anywhere towards answering this question about a computer devising a theory of everything. On the other hand, I kind of love this question. It reframes certain aspects of the scientific process and raises questions about what aspects of reductionist logic could be automated. And especially as you're starting to talk about the space of all possible anything, the space of all possible conformal field theories, quantum field theories, all types of different measurement strategies, exploring giant spaces are things that computers can do well. And it's a question about machine learning and AI, whether they could give us any handles in those directions, either more speculative theoretical directions or more practical applications relevant for experiment. So, my perspective, which continues to evolve over time, and I'll try to say this in this talk today, is that theoretical high-energy physics has been irreversibly impacted by the rise of deep learning. We can't go back, and there's certain things that we're now doing that I just can't imagine not doing using deep learning techniques. At the same time, there's a lot of buzz around AI, whatever that means, and about deep learning and, multi-layer neural networks. But my view is that we should be leveraging analysis strategies from various areas of mathematics, statistics, computer science. And some of the best conversations that I've had as director of this AI Institute has been with people who get mad at me for saying the words AI and ML. They say, no, what we're really doing is things like computational geometry. And I think that we have a lot to learn from those communities. And then for the discussion, we have an opportunity as a community to translate aspects of high-energy physics theory into a computational language. And this computational approach is one that I found fruitful in my research, and we've heard a little bit about it this week already. I want to tell you a bit more, at least give a chance for you to give your perspectives on how it might be relevant for your research. And as with a short talk like this, citations of this talk are representative and certainly not exhaustive. Okay, so to begin, I'm actually going to sidestep these first and just kind of step back and say, what the heck are we talking about when we're talking about machine learning? Some of you know what machine learning is. Some of you have probably know more statistics than I do. But what formalisms are needed to leverage machine learning for HEV theory? Like, what are we actually doing? We can, watch deepfake videos and be worried about robot apocalypses, but like when it actually comes to the equations that we're writing down, what are we actually writing down? And let me give you a super simple example that we can all understand, just to make sure that we're all on the same page. And for me, it's a deeply satisfying equation at the level of theoretical physics. So this next slide is not deeply satisfying. The slide after that, the one that's satisfying. So let me show you how this was introduced to me for the first time. So This is now kind of a statistics perspective. And a trick that's called the likelihood ratio trick, which I learned first from Kyle Kramer, a key example of simulation-based inference. And it's the goal to estimate a likelihood ratio between probability densities. So I have two probability densities, P of X and Q of X. I have training data, finite samples from this probability density, let's say drawn with a Monte Carlo program. And then some kind of learnable function, f of X, that's parameterized in some way. It could be a linear function, some nonlinear function, neural network, doesn't matter, something that has parameters that can be floated around. I compute a loss functional. In this particular case, I'm taking the expectation value over sample P of the logarithm of X, and the other one, I'm taking the expectation value of Q of f minus 1. And the claim is that if I have enough data, that is asymptotically, and if my functional f is flexible enough, then the loss functional is optimized when the f is this ratio P over Q, which is the desired outcome. And then moreover, the value of the loss is F divergence, called the Kullback-Leibler divergence. That's a usual way that we use to compare probability densities. Okay, so I see this and my eyes kind of glaze over. This is a stats language that does not make sense to me. And even like just trying to convince myself that this was true was difficult. But you know, once you translate it to a language that a physicist can understand, all this is Lagrangian mechanics. That is, we have an action. Okay, it's an integral over x and not t. We have a Lagrangian, and this Lagrangian depends on the probability densities p and q. And all we're doing is solving the Euler-Lagrange equation. And this happens to be a particularly simple one because there's no derivatives. And this Lagrangian, Euler-Lagrange, gives you the solution that you want. And once you realize this, you say, oh, all these people arguing in the literature about this, that, loss function, like all you're basically saying is what Lagranges can you choose that whose equations of motion give you some object that's of interest to you for your specific task that you're trying to solve. What this requires, though, is a shift in theoretical focus from solving problems to specifying problems in the language of optimization. But if you can do that, then machine learning gives you a numerical way, via what's on the previous slide, to achieve your goals. So kind of more generally, if you want to apply machine learning, here are the ingredients you need. And again, many HEB theory tasks can be phrased as some kind of machine learning optimization. You need some well-specified loss. This is where the theory comes in. You decide, not the machine, you decide what you want to optimize. And maybe you want to solve a classification problem, like what Ian was mentioning with identifying interesting radiation patterns from jets and classifying them as quark jets, gluon jets, something more exotic. Maybe you want to do a generation task where you want to generate synthetic data. That can be done in a well-specified loss. You need reliable training data, either real data, synthetic data. It could be data that you collect on the fly, data that you already have in hand. It could be streaming readout from a detector. And you need some learnable function, something that's flexible enough to model whatever answer you're trying to get. And a lot of physics can also come into this learnable function. For example, if you know that that function has certain symmetry properties, you can guarantee that the machine will only give you an answer that satisfies those symmetry principles. So physics input is essential for robust usage of these tools. You know, in the choice of loss, making sure your data is reliable, making sure your learnable function has the right types of flexibility. But interdisciplinary training is also valuable to know what types of optimization strategies people have developed in order to actually do this optimization. So let me give you an example of this, and I'm choosing a really unsexy example. This is not one of these things where you're going to see like robots dancing across the screen. This is something that is, you know, bread and butter things that we need to do at colliders. We need to, as we heard from Marius, think about Monte Carlo beyond leading order. And one challenge that you face when you're trying to build Monte Carlo generators beyond leading order is that sometimes you encounter negative weight events. That is, your leading order answer gives you positive events. You have quantum interference effects that can give you negative weights. Those together give you a physical answer that's positive, but the way that that's spat out by the algorithm is both a combination of positive and negative weights. When you have negative weights, that makes your procedure more statistically delicate. And so you'd like to have a positive weight Monte Carlo generator. So we can use this likelihood trick that I told you before. We have a sample of events with the correct physics, but some negative weights that we don't want. We have a sample with the wrong physics, but all positive weights that could be coming out of a garden variety Monte Carlo generator. You train your classifier, learn that ratio, that gives you weights, and you unweight your events such that an output from MC at NLO which would give you large weight cancellations between plus and minus 1. With this neural resampling, you can generate the, in this case, the number of initial state radiation jets, matches the distribution, as well as matching the statistical uncertainties using some trickery on the ML side. And when you're seeing an example like this, part of why I like this example is that it's just an algorithm. And unlike other cases when machine learning is used, for example, with jet classification, where you ask the question, hey, what did the machine learn? Like, what is it doing? What insights did it have? Here, you're not tempted to ask that question. You're just saying, oh, I have an algorithm. It spits out weight factors to correct my probability density. It's just reweighting. And in fact, a lot of the kind of hype about machine learning can be translated into, oh, it's just solving that optimization task. And in particular, what is the machine learning? In most cases, the machine is learning an approximate solution to a well-specified optimization problem. And then you say, well, okay, well, where's the physics? Well, the physics is, did you specify an optimization problem that's worth optimizing? And is the solution approximate? Is it good enough for the task you have in mind? And, machine learning is just, algorithms based on learning solutions to some problem that you want to solve through the use of data. So you need to have data already acquired or a strategy for acquiring data to use these techniques. Deep learning are algorithms based on learning parameters of some multi-layer neural network. And, these techniques are very powerful, but they may or may not correspond to our ideas of what, true artificial intelligence should be. Algorithms to perform tasks that are typically associated with intelligent beings. Linear regression is a algorithm based on learning solutions to data, but there's no kind of underlying meta logic for doing linear regression. It's not like it's a smart thing to do if you're a grad student, but I'm not sure that you would think about it in kind of the complex workings of the brain. And similarly, if we think about what we do as physicists, physics intelligence, algorithms to perform tasks that are typically associated with physics PhDs. Okay, I understand that this implies that intelligent beings and physics majors might not be overlapping, but in some sense, it's like some of the things that we do, is linear regression really a type of AI in terms of needing higher level reasoning, and is phase-space integration, which we do as physicists, that's something that we can do with deep learning. Do I really want to say that that's an AI technique? But I think it is true that we can push these kind of techniques closer together so that we're not just doing, eventually, asymptotically, not just doing these more simple optimization tasks, but meta optimization tasks, which might push us closer to this orange direction. Okay. So now let me come to some of the points that I want to make about the impact of machine learning on the theory frontier. So my talk is sandwiched between some talks from TF07, which is on collider phenomenology, and then later this afternoon, we're going to hear about lattice gauge theory. And one of the exciting developments that's been happening in lattice field theory has been using deep learning for sampling gauge field configurations. So as we all know, and we'll hear more this afternoon, the equations governing the strong nuclear force are known, but precision computations are extremely demanding. And I'm told it's something like 10% of open supercomputing in the US use these techniques. And my colleague Fiala Shanahan has been collaborating with Google DeepMind to build custom generative models, that is ways of generating gauge field configurations, based on normalizing flows, which is a machine learning technique to generate probability distributions, that achieve, at least in a toy example, 1,000-fold acceleration while preserving symmetries and guaranteeing exactness of the results, so that the results, at least asymptotically, will have the same degree of precision as we get from standard lattice sampling techniques. And it's exciting that these techniques also find interdisciplinary applications, because one of the things that we need in a lattice gauge theory context is we need to deal with compact gauge groups. And compact groups appear also in things like robotic arms, which have a U1 symmetry as the joints move around. And so this is just showing that improvement, and it's kind of the merging of deep learning with deep thinking. The deep learning side is normalizing flows, which is a computationally efficient way of doing essentially a change of variables. On the deep thinking side, imposing gauge equivariance to make sure your calculation has the appropriate gauge non-transformation properties at the end of the day. And something at the intersection is learning on compact domains, which is something that's relevant for both communities. I'm coming from the collider phenomenology, TF07, and Ian promised that I'd tell you a lot about jet classification, and instead, no, I'm just going to say jet classification, yes, that's something that we do, but there's actually a huge range of other things related to collider data analysis and collider theory that are taking advantage of deep learning. Parton distribution functions are being parameterized as neural networks and then optimized using data science techniques. Pilot mitigation sits at the boundary between theory and experiment, but you can view pilot mitigation as a type of regression task that machine learning is very good at. Parameter inference, which we can use using standard maximum likelihood techniques, but using simulation-based inference, that is, are also known as likelihood-free inference, basically not having analytic answers for what your likelihoods are, but just getting it from sampling. That's a way of also doing parameter inference, in this case, in extensions of the standard model. Parton shower modeling and tuning. You can build generative models that actually give you the sprays of particles in the same way that a Parton shower generator would do so. Phase-space integration. This is similar to what's happening in the lattice context I said before, where you're sampling configurations in a way that does better than like Vegas-style adaptive algorithms. You can approximate scattering amplitudes. Scattering amplitudes themselves are computationally expensive. You can use a machine learning tool to approximate those amplitudes. And then there's a trade-off between the level of approximation and the computational cost for evaluation. And then deconvolution techniques also on the boundary between theory and experiment, where we can correct the effect of noise using machine learning techniques. All of these are well-defined optimization problems. There's many more. And the point that I want to drive home is not the specific techniques that we're using. The point that I want to drive home is that progress is being made not just because of increased computational power and large data sets. I mean, yes, that is driving a lot of the advances in ML, AI more broadly. But here, we have progress because we're understanding the structure of the underlying problems. We are choosing loss functions. We're choosing network architectures that satisfy our physics goals. And the structure of many high-energy physics theory problems are often optimization tasks. And this came up in Eva and David's talks, as well as some of the discussion after Clay and Ibu's talks, that there's cases where we can apply numerical methods, and in certain cases, those numerical methods are related to optimization. Let me, in the interest of time, skip this. This is just a zoo of different network architectures showing that theoretical priors influence the choice of network architecture. Let me skip that just in the interest of time. Okay, so the next point that I want to make is that the buzz is around AI, but we should be really leveraging analysis strategies from various areas of mathematics, statistics, and computer science. And something that I had no idea about until I talked to my colleague Justin Solomon at MIT is that you can use a technique called optimal transport for understanding the geometry of collider physics. You can imagine these energy flows that Ian was talking about before, and instead of measuring correlators, where you average over a bunch of events, you can take individual energy flows and try to distort them into each other. And that's an optimal transport problem for distorting, in this case, the red energy flow into the blue energy flow. And that can give you a distance between energy flow configurations. That distance satisfies the criteria of the triangle inequality. You can use this to triangulate a space of collider events. And this is just a data science technique. It appears in people doing, for example, computer graphics. But remarkably, we've gained new insights into high-energy physics facilitated by advances in mathematics, statistics, and computer science. And remarkably, this, which sounds like, okay, why am I manipulating data? Why am I doing this optimal transport? What does that have anything to do with theoretical physics? And then you realize, oh, wait, we've already been doing this for 6 decades. This way of phrasing collider data analysis in the language of optimal transport gives us a rigorous definition of infrared and Clodier safety, gives us a new way of understanding event shapes that were developed in the 1970s, a new way of thinking about jet algorithms, jet substructure, even pilot mitigation. And this geometric approach then gives us a vector for how we might do analyses in the future. And it's interesting to think about how this, what I'm showing here, dovetails in what Ian was talking about in the previous talk. And the other thing that I want to emphasize is that this is an opportunity to open a dialogue between communities. Domain knowledge from high-energy physics, connecting with interdisciplinary insights. So for example, here at Santa Barbara, the group here has been analyzing jets with linearized transport and partial transport techniques. This is things that I had no idea really existed before reading Nathaniel and friends' papers. And then this is a case of a mathematics paper interpolating between optimal transport and kernel methods. And I'm coloring optimal transport in orange. That's the interdisciplinary insight. I'm coloring kernel methods in purple. HEP domain insights. What is, I don't, do people know what kernel methods are? You know, and the reason why is that this interpolation is an interpolation between moving dirt around. That's the optimal transport picture. And then doing an electrostatics problem where one configuration of energy flow is positive charge, the other configuration is negative charge. And you're actually calculating electrostatic potentials, exactly as we would do in a first-year physics class. So it's kind of fascinating that these things are related in this way. Okay, so let me wrap up with now some questions to you, talking about an opportunity to translate aspects of high-energy physics theory into a computational language. So, machine learning for formal theory. What aspects of formal theory could be rephrased as a data science problem, albeit with theoretical data? So for example, my IPI colleague Jim Halverson has been thinking about the relationship between neural networks and quantum field theories, thinking about both of them as theories of random functions, albeit defined in different ways. Are there other theory tasks that could be phrased, formal theory tasks that could be phrased in this data sciencey language? Machine learning for BSM theory. What aspects of BSM phenomenology could be streamlined, systematized, and automated? This is a picture from the LHC Olympics, which was a data challenge to try to find anomalous signals in mock data. What aspects of that search for anomalies, or even the statistical definition of what an anomaly is, what aspect of that could be kind of elevated to become a data analysis or data science problem? And then machine learning for standard model theory, what aspects of precision standard model theory could be more tightly integrated into the analysis pipeline? We had Ian's talk talking about open data, where you can use open data to explore new aspects of theories that and motivate experiments to do measurements. And we know that PDF extraction, that's an example of a more close collaboration between theory and experiment, because you need to use the experimental data to fit for PDFs. What aspects here might benefit from a more integrated data science approach end to end? So with that, in the spirit of Snowmass, I'm looking forward to your ideas and perspectives, and looking forward to dialogue right now and also at lunch coming up. Thanks so much.
Terrific. Thanks very much for the nice overview. Questions, discussion?
Thanks for the great talk. I have a kind of remedial question, and then I apologize if you already said it, but when you do, say, a classification problem to classify different types of jets or whatever it might be, how do you think about uncertainty quantification there?
Yeah, fantastic. So the question was uncertainty quantification. So you can think about all the various types of uncertainties. And here we can actually benefit from talking to our colleagues who think about ethical issues. And so this is a paper that is describing a framework for understanding unintended consequences of machine learning. And bias for us is what would be a systematic uncertainty. So now you can think about all sorts of paths, places where bias could creep in. It could be in the data sets that you're generating. It could be on the model assumptions that you're making. It could be related to the losses that you're choosing. It could be related to the data that you're using for training is not the same as the type of data that you're actually looking at. And this is an incredibly challenging problem, and one that we have to take more seriously. In some research that I'm doing right now, we're trying to make sure that the uncertainty quantification step can be done at the same time as, at least certain aspects of the uncertainty quantification can be done at the same time as the initial training. And you basically parameterize your neural network in a way that when it learns an answer, it learns the values and the uncertainties, at least in a certain limit, at the same time. But really figuring this out is something we need to work on. And some people say, oh, just do Bayesian neural networks. And I now have a more gut understanding of why our field tends towards frequentist logic, because it's really interesting to see how bias plays between different statistical methods, and then you just see that directly when you're doing the training. Bayesian style training versus more frequentist style training, there's an interesting trade-off that appears there. but this is a huge issue that needs to happen. In practice, what we do for uncertainty quantification is that you treat these classifiers as if they were just observables that God handed you, and then you do the standard uncertainty quantification as you would for a standard collider observable. I think we have a chance to do better and really integrate uncertainty quantification into the training task directly.
Other questions? Just as a reminder, please identify yourself if you're in person for the benefit of the online viewers.
I mean, I'm happy to throw in a question here. Again, this is Nathaniel Craig. So you've given us a lot of great examples where machine learning is making inroads in HEP, and there's some ongoing developments and future prospects. Are there aspects of HEP where there is not currently a lot of machine learning where you think there are opportunities?
Well, so these examples that I gave before are some of them. I think the example that I would love to be able to address most, if I said, and I'm not convinced that machine learning is the solution, by the way, at least to this uncertainty quantification question, is how do we do uncertainty quantification for theory calculations? You know, when we say we do scale variation up and down by a factor of 2, or we have RG scale choices, are there more principled, let's say, information theoretic ways that we might address those questions? And this idea of kind of integrating the data analysis and the precision standard model theory, we already know that there's certain things that we don't know, like PDFs, that we can use the data to help give us insights on. You can ask whether that might be relevant at all for the way that we think about perturbative calculations and addressing, for example, absences of higher order effects. I'm not sure that machine learning is the right strategy there, but it's starting to smell like that might be the right way, or just more generally thinking about it as an optimization problem, that when you do a theory calculation, that theory calculation has some truncation error. How do you think about not having that information? Is there a way of phrasing that as a machine learning task?
Thanks. Any more questions? Yes.
Thank you. Hi, this is Raja Bugazel. So in terms of streamlining BSM searches, have you thought of the idea of using what you have described to do global SMEF fits? This is one of the things that's driving the community right now, and it's going to be a very, very complicated problem for us to deal with. And I'm very curious to know if you have thought of this and how you think it would help in that direction. Yeah,
so the question was, could I do global SMEF fits using these techniques? And the answer is absolutely. If you have fully trustable data, real data and synthetic data, that is, you have a Monte Carlo generator that for every value of the SMEF parameters can spit out arbitrary amounts of data that would correspond to those, then it's a very straightforward maximum likelihood procedure to draw those contours. And this thing I was just mentioning about trying to do uncertainty quantification in kind of one shot, the thing that we're working on would give you in principle kind of error ellipses in the Gaussian approximation kind of immediately with one neural network training. But the key thing is having the trustable training data. I'm having a fascinating conversation with a statistician at MIT who was bemoaning the use of cut and count by the high energy physics community for kind of separating things into signal and background regions, and saying, you idiots, don't you know that the optimal thing to do is this other thing? And the statistician is correct. There's a better way of doing things than our standard cut and count. However, then he comes back to me and says, well, you know, maybe you guys aren't so stupid after all, because maybe you actually have imperfect simulations. And maybe under a certain model of the noise, actually what you're doing is optimal. That is, cut and count can be an optimal analysis strategy in the presence of certain types of noise. And so then you start thinking, okay, when I'm trying to model my uncertainties on what is the standard model, what is the standard model when I deform in SMEF space, can we think about that and the uncertainty model and actually figure out what is the optimal signal regions to choose, and then we could do this likelihood effect accounting for also the noise model. So I think it's interesting to think about. And then the SMEF case, I mean, that's basically what this parameter inference example is here. And these are different ways of setting confidence limits that agree in the rough amount, but disagree in the specifics about different ways of doing this simulation-based inference. And so this CU and CG are, well, not really snuff parameters, but related. Yeah.
All right, great. Well, we are perfectly on time for the end of the session. Maybe one more quick question.
Sorry, I was behind you. Hi, this is Aida El-Khadra. That was a really, really nice talk. You showed that slide with the LHC Science Olympiad.
Yeah.
I'm wondering if you could comment a little bit on the lessons that were learned in that exercise, which, as I understand it, not all of the analyses did very well.
That's right. And one of the best analyses was done by a team of cosmologists and not by high energy physicists in terms of actually getting the expected significance on a signal. The lesson that I took away from this, so first of all, am I allowed to just grieve here? My team was declared to have been the biggest loser in this, okay? And this irks me because what we discovered is that there was a dramatic mismodeling of the background. And we actually discovered in the data something that was so weird that we said, this is like a huge, I can't remember, it was like 400 sigma effect. And what it was the organizers who did this flipped some switch in Pythia to try to change the background in a way that was not consistent with the physics model. So we discovered that. We discovered that using deep thinking, and it's like a huge problem in the background modeling. Okay, so that was one issue that I learned, is that background modeling is important. And if you just look under the lamppost, you can miss these gigantic issues. And it was the jet physicist in me that said, oh, let's look at some of the more generic features. And then you saw dramatic mismodeling. Okay. But the other lesson that I learned is that we don't have a precise definition of what it means to be anomalous. We have a variety of different intuitions about what anomalies are. We think about anomalies as being bumps or maybe edges or features. There's certain cases where this can actually lead to some confusions. And in particular, certain anomaly detection techniques make assumptions of what it means to be anomalous. So I see, Yoni's in the back of the room, and he's written a paper about, basically under certain cases, you can completely excise a region of phase space. And certain algorithms for anomaly detection won't even know that anything's missing, which seems to be somehow wrong. And that's because we need to have a precise definition of what we mean when something is anomalous. And that's a theory question. And one that we have a chance of really defining. And then when we're saying streamlining, systemizing, and automating, let's take the lessons that we have from specific models, what that looks like as anomalies, and then try to generalize that for signatures that we haven't thought of before.
All right, thank you. So I'm sure there's many more interesting discussions to have here, but I think let's have those over lunch. So we'll close the session out. Let's thank Jesse and all the speakers once again.
Okay.